It's for Landon. He's not here, so everybody's not ahead of Landon. And then Taylor, and Audrey, and Justin. All right. So the next unit is harmonic motion, which is primarily the motion of things that vibrate or bounce, like a pendulum or a spring. So I got a spring right here. You might realize this is a, what kind of spring this is. It's a bouncy spring. Yeah, it's a slinky. And springs have a spring constant, which expresses their stiffness. So slinkies have an extremely small spring constant. They're not very stiff. Well, the springs in your car, there are 4 of them, or 8 of them, depending on what kind of vehicle you have. There are at least 4. Those keep your car from basically bottoming out when you go over a pothole. They have spring constants in the tens of thousands, whereas a Splinky's spring constant is like 1/2. Okay, and the spring in your mechanical pencil, that's like in the less than 1 as well. Boop, boop, boop. Not very much. Doesn't require a lot of force to get it moving. But here we are. So, and we also talked about period and frequency before. Period is the time for one bounce. One complete cycle, one up or down. So I put a mass on it to give it a little more stability. So let's just pull this down, wait for it to kind of settle out a little bit, and then we're going to let it go. Okay, I'm going to let it go from down here. So after it completes one period, tell me to stop. I'm going to start in just a second. Ready? Start.
Now.
Yeah, good. So once it starts repeating its motion, so if it goes down and it's on its way up, on the start, it should be on its way up on the next cycle. So that's one period. So what? And there's one. And there's 2. Okay, so that's a period. Pendulums work the same way. One back and forth is one period. So if I took the pendulum and I swung it this way, if it starts there, then where should it stop? There.
It's a nice softball.
Yeah, it's a green one. Yay, softballs. I have a bowling ball, but nowhere to put it. I can do the bowling ball thing, but nowhere to put the bowling ball. So you can do this yourself. You can where you have the thing, and you're like, hold it right there, and you're like, don't move. The important thing is you don't move. Okay. So normally you've seen this on YouTube, right, or on TV, where they take a bowling ball and they put it up to a girl's nose, and it's like, oh, don't move! And then it comes back and it like wipes her out. No, it doesn't hit her, right? It shouldn't hit her because she shouldn't move, but this one, you're like, boom, she moved! So like, there's her nose, like right here to start out. And then she moves over. It's, fun. Totally torpedoed that physics guy. If you go to the Oregon Museum of Science and Industry, they have a really cool gigantic pendulum that you can go up on like the 2nd and 3rd floor, look down at, and it's called a Foucault Pendulum, named after this guy named Pendulum, and he was from France, and he has this gigantic pendulum, and it's very, very heavy, and he swings it, and it's able to swing freely. And the one in the museums have a little motor that keeps them swinging so they can counteract friction in the hinge, but it's used to tell time. How is it used to tell time?
They can set it to where it'll bounce 60 times per minute, so then
it's a freely swinging pendulum. Swings and swings, and the idea is it has a whole bunch of momentum. It's very, very big. This is a giant ball. Sometimes it's hollow, but a giant ball of steel. It weighs several tons, and then they put pins all the way around it, and it just knocks over the pins constantly. Usually they put like 180 or 360 pins, so it's like knocking them over every 15 minutes or so. It keeps knocking them over, and then someone has to go put them up again. But that's how you could use it to tell time, because it would keep going back and forth, and the Earth would spin under it. I've often wondered if a Foucault pendulum would work on the North Pole.
Why?
Because the spin is a bit different. Yeah, it's one of those things like, I'm going to have to look into it. Well, Foucault pendulum work on the North Pole? But it works great in France and it works great in Portland, Oregon.
Field trip.
Yeah, field trip. Everybody going to the North Pole.
Okay.
Get your field trip permission forms in. Okay. Now, this is kind of neat, and this is actually the segue unit to waves. And that's where we're going with the next unit, is sound waves and light waves. So we're going to transition from mechanical things to air, so mechanical things that are vibrating to air that's vibrating, and then electrons that are vibrating. So that's where we're going in February. We're going to talk about waves. But it turns out, if you have a bouncing pendulum, and you look at that pendulum over a consistent x-axis, the y-axis will draw out a sine wave. It's what we call a sinusoidal motion. So just like this pendulum, it's bouncing up and down. If you allow a pendulum to freely bounce and you draw an x-axis that is constant, it will draw out a sine wave. If we put a little marker on this and then had someone bring a piece of paper somehow that didn't have enough friction that would keep going, then it would actually draw out a sine wave. It's actually kind of neat. So a sine wave, a sine, like sine versus cosine. So sinusoidal is that shape. So this shape pops up a lot. But if you were to look at this and like if you were to fix your motion, there's a light on it, and you went this way, you would see a sine wave on the pendulum, or it's straight. Yeah.
Is that how the sinogram works? The thing I mentioned earlier?
Kind of. Yeah, pretty much the same idea. A lot of things are like they have a consistently moving x-axis, and then something causes something to move in the y-axis. That's basically what that is. It's basically taking small vibrations and amplifying them, usually electronically. So that's also how like an EKG works, where they look at your heartbeat or your brain waves and they amplify them. Okay, so moving on. Any other questions before we move on? I don't have a good Newton's pendulum, but this is what it's called. It's called a Newton's pendulum. That clink, 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 that annoying thing, clink, clink. That's called a Newton's pendulum. Or Newton's cradle, sometimes too, Newton's cradle. I've never actually got a good one that I liked that didn't just like get crappy after a while. Yeah.
Is there a giant version of that?
No, because the vibration doesn't scale. The Mythbusters actually did a video where they tried to make a giant Newton's cradle, and what we found is the vibrations through the steel ball, they don't scale. So the small ball thing will click, it'll stop moving and keep going. It'll transfer all of its momentum to the next ball. With the big one, it hits and there's just too much vibration in the large steel, so it doesn't transfer all of its momentum. So yeah, it's crazy things that things don't scale in large sizes. So a tiny Newton's cradle will go boop, 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 and then you get like a bowling ball and it doesn't work because the bowling ball, or even if you have a bowling ball sized chunk of steel, it still doesn't work. It doesn't scale up. Because the vibration has to move through the molecules. So if you get a tiny steel ball, maybe you only have 5 billion molecules across. With a large steel ball, you have 500 billion molecules across, and that vibration has to go from molecule to molecule to molecule to molecule to molecule. You know what the ultimate failure in scalage is? The sun. We took an H-bomb with an amount of fuel about this big, and we blew it up, and it went bam, done. The sun's been doing that since the beginning of time, and it'll keep doing it for another 100,000 years. The exact same fusion reaction that we did out in the South Pacific, boom, the sun's been doing for hundreds of thousands of years, and it'll keep doing for hundreds of thousands of years, or however long the universe has been around.
They said it's been like.
It might have been billions, it might have been millions, it might have been thousands. It's entirely up to your vision of whether my pointer's going to work or not. Okay, so periodic motion. Let's talk about pendulums. So we got our pendulum hanging out here. There is a formula. There is a formula for periodic motion. It's just, when we talk about periodic, what we're talking about is something that happens in regular patterns. Like last you learned about the periodic table. Periodic because it's at patterns. So periodic motion is something that has a pattern that repeats and repeats and repeats. Harmonic motion is basically used as a synonym for periodic motion. It's just simple back and forth motion. And something that is important about periodic motion is the restoring force, something that moves it back to its equilibrium position, has to vary with that distance from the equilibrium position. That's Hooke's law. Hooke's law, remember that F equals negative px? So Hooke's law is F restoring negative kx. K being a spring constant, x being the distance from the equilibrium. So that's for Hooke's laws for springs. You use weight, we're talking about pendulums, we'll get there. We'll have a simulation about that. But that's the important thing is, as you get further from the equilibrium position, you have more restoring force. If I pull this weight down, way down away from the equilibrium position, there's a lot more restoring force, as evidenced by a lot more acceleration. So much so that the weight just popped right off. And similarly with a pendulum, if you move a pendulum not very far from its equilibrium position, like beep, its acceleration is very small because the restoring force that is a component of gravity is very small. But if you move it really far from its equilibrium position, then it has a very high acceleration because its acceleration is a component of weight. In fact, if I was to be able to lift this up at near 90 degrees, its acceleration would just be what? Yeah, g, it'd just be g, if I could get up there. As it is, all you really have to do to find out what the instantaneous acceleration is look at that angle, and then just take a trig function of that angle. Which trig function should you use?
Sine.
Should you use sine? So when the angle is 0, it's g. So is it sine or cosine?
I think it's sine.
It's sine. Yeah, it's sine. Because remember, if you have 0 angle, then your effect is 1. That's sine. Sine of 0 is 1. If your angle is 90 degrees, your acceleration is 0, and that's also sine. Sorry, what?
You could use the ladder.
I could if there was a protractor. Maybe we will. We'll see how much time we have for today. Okay, so equilibrium position is the resting position where the forces are in equilibrium. Okay. We've heard that word before. Equilibrium basically means all the forces are canceling out. So the equilibrium position is where all the forces are canceling out. The ups, the downs, the left, the rights, they're all canceled out. With a spring, it's the weight versus the restoring force. With a pendulum, it's the gravity versus the tension. So the restoring force is the force that brings something back towards the equilibrium position. And then, of course, period, frequency, and amplitude might be a new word for you. Amplitude is the oomph, how much energy something's carrying. In simple terms, amplitude is the distance from equilibrium. Amplitude for a spring is pretty easy. It's just the linear distance, linear displacement, just how far you are. Amplitude for a pendulum is a little more dicey because I've seen amplitude expressed in degrees, angle away from equilibrium, I've also seen amplitude expressed in meters, as in like distance from the equilibrium point. By that, let me show you what I mean. So I'm not going to say amplitude is this or this because I've seen it expressed both ways, and it depends upon what your professor wants you to do or what you're measuring. But I have seen amplitude measured as this interior angle to equilibrium from this point to the equilibrium point, like this angle. I have seen it as expressed as that. I've also seen it expressed as a distance from this point linearly to this point, like an x distance. So I've seen amplitude expressed that way. I've also seen it expressed as an angle. Just as long as you know that amplitude is the distance from equilibrium, you can use trigonometry or basic geometry to determine what it is that they're looking for.
I can do trigonometry and basic geometry. I is a smart guy. That's MRT. Smart.
All right, how are we doing so far? Scribbling everything we see. Did you really have to write down what period and frequency were? No, I just like writing things down.
Too late.
It's like I just came from an English class or a history class, so they want you to write down everything you see. Because they have this crazy. Is this still the case? Do you still have teachers who are like,
Yep.
if it's important enough for me to put it on the board, it's important enough for you to write it down. Still have those teachers?
I never write.
Yeah, neither did I. No, I learned it too late in high school and college that the best thing to do is scribble down what your thoughts are as you're going through the unit. If you understand it, then write it down in your own words. If you don't understand it, then you need to ask questions. Do you understand it? Do you understand these concepts?
I'm all going back and forth.
Okay. Shall we move on? Waiting. Okay. We're moving on? Moving on. Okay, so let's rub a little math on the pendulum thing. I'm not going to go through the derivations for you. This is one of those equations where you're like, oh, yeah. Woo, and here comes the bowling ball. Bam.
Wait.
She came in like a wrecking ball.
Probably.
I love animated GIF files. Anyway, so I'm not going to do the derivation for you. I'm just going to give you the equation and let you use them, assuming my battery is any good. So this is the formula for the period of a pendulum for small angles. For small angles, in other words, angles small enough that we can ignore air resistance and friction and all sorts of other crazy momentum effects and inertia effects. For small angles, it's 2 pi the radical L over G. Length over gravity. So again, and I'm not going to do the derivation for you about how this is related to things moving in a circle. Just realize it's 2 pi radical L over G. So this begs the question, if you have a wrecking ball and it's swinging along and it has a certain pendulum of natural swinging, does it matter how far, practically speaking, does it matter how far it is from the equilibrium point? In other words, if I had a pendulum swinging like this, would this have the same period as this?
Yeah.
Okay, let's go back to our equilibrium point. If I have a pendulum, a simple pendulum, and I let it swing like this, does this have the same period as a pendulum with a bigger amplitude?
Yes.
It does. Do you see amplitude anywhere in the formula?
No.
No. So amplitude is not in the formula. So because amplitude is not in the formula, amplitude does not change the period. And therefore, also doesn't change frequency. Okay, does that make sense?
How does that work? Because with one with a larger amplitude take more time?
I'll ask you this. If you jump off a diving board into the pool, and somebody else just walks off the edge into the pool, do you both accelerate downward at the same rate?
Yes.
Yes.
Yes. Even though one's going further, gravity's still going to act on you exactly the same way.
Oh.
Okay, same thing. So even though one is further from the equilibrium point, gravity's still gravity. It doesn't matter. Okay. So what it basically means now is if you have to go further away, you have a larger component of gravity being acceleration. Okay. Does that make sense? So I have to go further away, but there's a lot more of the component that's going to move it towards the center is a lot larger component of gravity.
So it moves faster.
Yeah, it accelerates faster.
So it's the same amount of time.
Yep. Because of Galileo. Also, that's a segue to the next thing. If you have that wrecking ball, and Miley jumps onto the wrecking ball, if she just jumps straight, like falls onto it, or just gets onto it and then somebody swings it, does the wrecking ball have the same period as the wrecking ball with Miley Cyrus?
Yes.
Yes, because do you see mass anywhere up there? No. Mass is not in the equation, so mass, wrecking ball with Miley and wrecking ball without Miley will have the same period.
Did I do that backwards?
Freak out?
We're learning about
Yes, you're doing stoichiometry. Yeah. Mr. Schultz is a super cool guy.
He is really.
All right, so next, length. Changing the length does change the period. There's something kind of interesting. As this thing swings, I'm going to try my best to grab it and watch what happens. Yeah. So if I get it swinging, and then I grab it, so like doot, 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 doot. Good. So yeah, if I get it swinging and I grab it to reduce the length, if the length decreases, the period, because they're both the numerator, the period
Decrease.
Does the radical matter when you're looking at relationships? We're looking at increasing and decreasing. Does the radical matter?
No.
Not really. Okay. All that does is change the magnitude. So if your length decreases, then your period decreases. On the other hand, if you take the same pendulum to Mars, where gravity is 5/6 that of Earth, the G would decrease and the period would increase. Okay? If you take that same pendulum to Mars, the G would decrease and the period would increase. If you took this pendulum to the Moon, where the gravity is 1/6 of that of Earth, then the G would really decrease and the period would really increase. On the Moon, it would be like, that doesn't even look right. It's going way too slow. Kind of like when you see the astronauts jumping on the Moon, you're like, that doesn't look right. They're moving way too slow. They're moving way too slow because gravity is only 1/6 that of Earth.
Nice.
Part of the fun thing is like, it's easy to remember. Mars is 5/6. Moon is 1/6.
Easy.
Add Mars plus Moon, you get Earth. Okay. So now at its highest point, let's look at some vectors here. At its highest point, basically at the pendulum's highest point where the amplitude is a full 90 degrees, or L or 90 degrees. At the highest point, you have a velocity that is 0, it comes to a stop, but the acceleration is g. Because the acceleration of a pendulum is what trig function times g? Sine g. And at 0 degrees, sine is, sorry, at, yeah, 90. Sorry, at 90 degrees, sine is 1. Yeah, 1. So A is sine g. So at 90 degrees, G is, or A is just G. And then as the pendulum falls towards the equilibrium point, the V is going, how is the V changing as the pendulum falls towards the equilibrium point? The V is increasing because there's a constant acceleration. And remember, way back to August, when V and A are the same sign, what is happening to V? It's getting bigger. And when V and A are opposite signs, what's happening to V? It's lessenizing, yeah, it's getting smaller. So as A and V are in the same direction, the V is getting larger, 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 larger. What's happening to A as it falls towards the equilibrium point? It's getting smaller because this angle is getting smaller, so the sine of that angle is getting smaller until that angle at the equilibrium point is 0, and the sine of 0 is 0.
I said 0.
Yeah.
I said 0.
Okay. So at the equilibrium point, so velocity is speeding up, acceleration is slowing down. At the equilibrium point, you have a situation where your acceleration has arrested. There is no more acceleration because there is no component of gravity pointing in the direction of the motion. But your velocity is maximized. The whole time it's falling towards equilibrium, the velocity is getting faster, 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 while the acceleration is getting slower, 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 slower. Until it gets to the equilibrium point, velocity has gone as fast as it's going to go, and acceleration has just come out to end up being 0. then the system reverses itself much like a bouncing ball. As the pendulum moves away from equilibrium point back towards its highest point, what happens to A? A is increasing. What happens to V? V is decreasing. So now you have a situation where the velocity is going up as a positive value. Acceleration now is a negative value because it's retarding the velocity, and that makes the velocity go shrink, shrink, shrink. So as it travels past the equilibrium point, the velocity is slowing down because the acceleration is rising in the negative direction. It's becoming more and more negative, slowing down, slowing down, slowing down, slowing down, until it once again stops, and the process just flips itself over again, and you have increasing velocity